Okay, so let's continue from Monday's lecture. Okay, so let's continue from Monday's lecture. Okay, so can everybody see my screen? Okay, so you can see my screen, right? Okay, so let's continue from Monday's lecture. Okay, so today is the 26th. Okay, so Monday's lecture, we have been talking about the basic examples of differential equations. Okay, so say the basic examples. Okay, so basic examples of differential equations. Right, so on Monday's lecture, we have been talking about these basic examples of differential equations. And we have seen that in many natural scientific practical problems, differential equations helps us to model many physical or natural or societal phenomena that can be described by rates, right? So if you watch Monday's lecture, we've been talking about the slope and the rate of change of a certain quantity. Okay, so if this rate of change are related by an equation, then you're going to end up with such a equation of rates that we're going to call it a differential equation. Okay, so that we're going to call it a differential equation. Okay, so now, so there's in general, we define a differential equation to be an equation that contains derivatives. Okay, so, and we've been talking about an example on Monday, okay, so, which is about a certain kind of prescription drug and how it is administered in a person's bloodstream, right? So, and we have seen that the underlying principles for this problem can be described by this very simple relation that the net rate change of a certain quantity is the net rate inflow minus the net rate outflow of the same quantity. And by this principle, we can describe this equation by calculating the inflow into the via the inflow concentration multiplied by the inflow volume. Okay, so and with that we have end up with a differential equation that really describes the evolution of the amount of drug in the person's bloodstream. Okay, so and even without solving such a differential equation, we're able to predict the long-time behavior as you described here. What's the how much of the drug it will be present in the bloodstream after a certain long time. Okay, so and we have described it by certain kind of equations. I mean, from this equation, we calculate its equilibrium. Okay, so and on Monday we've been talking about the fundamental steps of mathematical modeling via differential equations, right? So basically, it is first you have to find the principle or law underlying the given problem. And once you have that, you have to decide the variables and parameters. So on Monday's lecture, we've been talking carefully on variables and parameters. Okay, so by variable and parameter, it simply means that which one is the function. Okay, so like what happened here, the differential equation is always describing a function as a function of a variable, right? So and this function has a derivative which is involved in the differential equation, and you just want to solve this function as a function of a given variable. Okay, so that means you want to determine the variables and parameters, and then you write the law into a relation between the derivatives. That's what we call a differential equation. Okay, so that's kind of a brief review of what we have been doing on Monday's lecture. Okay, so that's kind of a brief review of what we have been doing on Monday's lecture. Okay, so now let me come to our second topic. Basically, at the very beginning of his lectures, I'm going to give you, okay, so I'm going to give you a way that we can directly solve any kind of differential equation. Okay, so basically, it means that we want to solve, okay, so solve, okay, so any differential equation, okay, so we want to solve any differential equation directly, geometrically. Okay, so I'm going to say geometrically. So that means, how do I solve any differential equation geometrically? Does it mean this is the end of the semester? Well, this is the beginning of the semester, right? So indeed, it's the first time you come to such a live session of this class. So it's not the end of the story, right? So, I mean, but it's the beginning of the story. However, my point is that even at the very beginning, I'm able to give you a method that solves any differential equations. I mean, presumably, theoretically, or in a certain sense, ideally, solve any differential equation that you might encounter. Okay, so but this is a very general method that we will talk about its drawbacks. Okay, so now in order to solve such a differential equation, let us first try to write down a differential equation very generally, right? So if you want to write a differential equation generally, let me write it as dy over dx is equal to f of x and y. So that's a very general differential equation, right? So what does it mean? So you have to first know, okay, so at the very, from the very beginning, you have to know that which one is the function and which one is the variable. Okay, so for example, for this differential equation, you must tell me we are looking for x as a function of y, or we are looking for y as a function of x. Anybody can tell me? Okay, so you can tell me what you think by just unmute yourself and speak loudly. Okay. So can you tell me we're looking for a function y as a function of x or x as a function of y from this differential equation? Anybody has idea? Anyone has idea? Okay, in order to speak, you can just unmute yourself and you can speak loudly, then I will hear you. Okay, so right, so anybody has idea? Okay, it doesn't matter. Okay, so we're looking for here, what happened here is that you're looking for the function y, right? So as a function of x, so y equal to y of x, right? So you're looking for the function y as a function of x, right? So, and in order to have this, right? So you can just, let us just imagine that we already found a solution, right? So let us just imagine that a solution has already been found for this differential equation. Then you can describe the solution. Okay, so you have x here, you have y here, right? So you can describe the solution as a function y equal to y of x. So that means this is a function which looks like this. So y equal to y of x, right? So you're going to have the graph of this function. That's a geometric. The graph of this function must be some kind of a curve, right? So in the xy plane. Now, what does this the equation tell you geometrically from this graph? Well, you have to first interpret what is dy over dx, right? So suppose you're at the point x, right? Suppose you're at point x here, and how do you describe dy over dx? Well, it's very simple. You should draw a tangent line, right? So a line that's tangent to this curve, right? So a line that's tangent to this curve, and then the slope, right? So the slope of this tangent line is going to be equal to dy over dx, right? So the slope of this tangent line is going to be equal to dy over dx simply by simple calculus, right? So from our knowledge in calculus, we just easily know that the slope is equal to, the slope of the tangent curve is equal to the derivative, right? So it's equal to derivative. So that means the meaning of this equation, it simply says, okay, so this equation, it simply says that slope is equal to fxy. So what happened here is that you can think of this whole problem reversely, right? So you think of this whole problem reversely. That means in an xy plane, okay, so in an xy plane, suppose you are in an xy plane, then at every point in the xy plane, suppose this is the point x and y, then you are going to have fxy, right? So once you know x and y, you're able to calculate fxy because f is a given function, like what happens here, right? So you're going to be able to calculate the function fxy. And then regarding this fxy, we can draw such an arrow that points to the right direction with the given slope. So that means this slope, okay, so the slope of this arrow, which is given by of arrow is fxy. So that's a given slope, right? So that's a given slope. So it's like here, for example, at this point x and y, right? X and y, the slope is given by some fxy. So the slope should be equal to fxy. But we know that if there is a solution to the differential equation, it must be tangent to the slope direction at point xy. So that means the solution might be either like this or maybe like this, but it has to be tangent. I mean, the tangential direction of your curve has to be aligned with fxy so in such a slope at point x and y, right? So at point x and y in space, right? So that means this is kind of, in this way, we can give such a method of solving differential equation. Namely, when I vary x and y, when x, y varies at different points, there must be different slopes. For example, I mean, at every point in the space x, y, I'm able to calculate a slope because I can calculate the fxy. I will always have the slope, right? As long as I have all the slopes, I can regard my solution. Okay, so suppose I have a solution to the differential equation. Let's say this is the solution. By solution, it means that at every point of this curve, the slope is just the given slope is just a tangent to the solution, right? So a given slope is just a tangent to the solution. So in such a way, if you have every point, okay, so for every point, okay, so for every xy, right? So for every point xy, calculate, okay, so calculate a slope, okay, so the slope is given by fxy. And once the slope is given, we're going to draw an arrow starting from point xy with the slope fxy. We have such an arrow. Okay, so now for all the different points x and y, when all these arrows are given, such a field, okay, so such a field, it means that for every point xy, there is going to be an arrow given, and such a field is called a slope field. Okay, so right, so by slope field, it means that you're given the slope of your fxy, right? So directs to the slope at every point that you know. Okay, so the slope field is sometimes also called a direction field. Okay, so a direction field. Okay, so the slope field is sometimes also called a direction field. So by this, it means solving a differential equation. Okay, so solving a differential equation, right? So solving a differential equation is the same thing as finding a curve, right? So finding a curve tangent to the slope field. Or direction field at every point on the curve, right? So that means solving a differential equation simply means you want to find a curve that's tangent to the slope field or the direction field at every point xy on that curve. Okay, so that's kind of a general idea how you're going to solve a differential equation uniformly, right? So no matter what differential equation you have, it must have a general form that dy over dx is fxy, and as long as you have that, you based on the fxy, you can define such a slope field, and solving this differential equation simply means that you found a curve that's tangent to the slope field or direction field at every point on the plane. Okay, so here I want to show you some examples. Okay, so here I want to show you some examples. For example, let us consider this differential equation. Okay, so the differential equation has the form dy over dx is equal to 1 minus x multiplied by 1. Now, without even solving this differential equation, can you find the slope field? Well, the slope field is something like this, right? So now let me say I want to draw such an approximate direction field. Okay, so direction field. I want to draw a very approximate direction field. So that means I'm going to take a fine grid, right? So by grid, it means that I kind of cut this plane into pieces of rectangles, small rectangles. Now at the vertices of these rectangles, I'm going to draw such a slope, which means an arrow, right? So which means an arrow. How do I do that? Well, very simple. For example, the right-hand side looks like 1 minus xy. So that means if you're on the, let's say, y-axis, suppose you're on a y-axis, no matter where you are on the y-axis, your slope is going to be 1 because y now x is equal to 0. So the slope is 1. So you must have a 45-degree slope field along the whole y-axis. For the same rationale, you're going to have 45 degrees along the x-axis, right? So that's 45 degrees direction. Now, as long as your xy grows in the first quadrant, right? So as long as your xy grows in the first quadrant, your x multiplied by y is going to be larger and larger. So 1 minus xy is going to be more and more negative. So it's natural to see that your curves, your arrows are pointing downwards more and more. So that's kind of very natural to see such a trend of the slope field, right? So, and a similar rationale, for the similar rationale, you can work out the second and third and fourth quadrant, right? So for example, for the second quadrant, if x is very negative and y is very positive, x multiplied by y is going to be a huge negative number. When you plus 1, it will be, we take a negative sign and plus 1, it will be a huge positive number. So that means the arrow is going to point upwards more and more. So you're going to see pictures like this. Right? So that's kind of an intuitive picture that gives you such a slope field. Okay, so that's a slope field. Okay, so now with this slope field at hand, we want to say how do we solve differential equations. Okay, so it's like what I described here. By solving the differential equation, it means you want to find the curve that's tangent to the slope field, right? So how do you solve this differential equation in such a way? Well, here you can see that for example, I want to find a curve, but it looks like there are many arrows, and I can have arbitrary curves. For example, if I start here, then I'm going to have a curve probably going on like this, and then going down, some kind of curve like this. But if I start from here, then probably I'm going to have another curve. You can approximately see the trend of this curve, right? So basically, naively, you can think of the slope field as a wind, right? As a wind pointing to a certain direction, and you put a piece of paper in the wind field, and then it is going to flow along the wind field to somewhere, right? So that's, and the trajectory of the flow of this small piece of paper is a solution of a differential equation, right? So that's kind of what happens to the intuition. But then you suddenly realize, as we just pointed out, that you might have different curves corresponding to different, passing different points in this field. So that's what happens to this problem. Well, the problem means that you have to prescribe, this is what we call it initial conditions of this problem. For example, I want to have a solution that passes 0 and 0. So y of 0 is equal to 0. So that must pass the origin. If you want to have a solution that passes the origin, it must go somewhere like this and then go down, and it must go somewhere like this and then go down, go up, right? So that's kind of solution. In the same rationale, I can have a solution y minus y is equal to 0. That means I pass the point x is equal to minus 1 and y is 0. So that must be somewhere here, right? So you see the mouse is pointing to this point. X is minus 1, y is 0. So you're going to have a solution that probably goes up first and then go down. And similar rationale for y2 equal to 2, it means you're going to pass the point 2 and 2. So 2 and 2 might be here, so you must go down, and if you go reversely, you must go like this. So if it's 0 and minus 4, it means x is equal to 0, y is minus 4. You're going to have a solution that probably goes like this, and then in that direction, it goes like this. Right, so that's kind of from the slope field, you can approximately draw the curves of your solutions to the differential equation, at least geometrically, right? So, and in practice, for example, you can program, right? So you can write a computer program, and for example, in MATLAB, and you ask MATLAB to give you the slope field, right? So as long as it gives you the slope field, as long as your grid is fine enough, you can always trace the trajectory and see what's the solution, how's the solution going to look like, right? So it looks like from this point of view, we have already found a solution, right? So we have already found a solution to everything about differential equations, right? So it looks like all the differential equations are being solved, right? So just by trying to see a slope field. But now you can see that this method is not analytical, right? So it doesn't really give you the quantitative version of your solution, but rather it only gives you a trend of the solution, right? So you cannot really have a very precise understanding of how the solution is going to look like analytically, but rather you only know that, for example, it grows up and it goes down, right? So you only know like the qualitative properties of the solution. So that's the drawback of direction fields or slope fields in our problem, right? So, but in any case, this is really a way to solve differential equations. Okay, so this is in any case, this is really a way to solve differential equations, right? So at least we are able to find solutions to differential equations via the slope fields. Okay, so via the slope fields or via the direction fields. Okay, so now here I would like to say, okay, so I would like to say that there is a student resources webpage. Okay, so let me repeat that. For Monday's lecture, I already mentioned it. Okay, so, but I would like to mention it again. Okay, so there is a student resources webpage that you must be able to make use of from Canvas. Okay, so there are two web pages for the course. One web page is for our course. You go to the panel like 3304 semester. This is what you see here. What you see here, it contains the semester's syllabus, everything. But if you go to, okay, so I already talked about Monday's lecture, but if you go to courses, okay, so you go to Canvas courses and then all courses, okay, so you go to all courses and browse more courses, okay, so from the browse more courses, you're going to see the student resources webpage for the course, okay, so now for the student resources webpage, here you can find a lot of useful documents that will be helpful for your preparation of the exams of this class. In particular, there are exam 1 archived ODE exams that you must make use of. Okay, so you must make use of in preparing the exams for this class. Okay, so I would like to tell you that in our lectures, we're going to make a lot of use of this previous year's exam problems just in order to help you. Okay, so just in order to help you to prepare better for the exams. Okay, so for example, here today, I would like to show you, okay, so one of our past semesters exams regarding the slope field. Okay, so we had there was one time we had a pretty nice problem on the slope field. Okay, so there was one time we had a pretty nice problem on the slope field that I would like you to see. Okay, so I would like you to take a look. Okay, so here, okay, so let me try to find it. Okay, so yeah, so this problem. Okay, so this is a pretty nice problem. Okay, so and here, so today is the second lecture, but I would like to already start talking about exams. Okay, so this is how our exam is going to look like. Okay, so as I have mentioned, as we have mentioned in the beginning of these lectures, there's going to be 3 midterm exams and 1 final exam throughout the semester. Okay, besides your homework scores, most of your credits received from this class are based on your performance on this exam. So they are very important for determining your grade for the course. Okay, so now how does the exam look like? Well, you can see this is the first page of an exam. Usually, our first exam consists of 5 to 6 problems, which is summing up to 100. Okay, so for example, this exam has 6 problems and sum to 100. You have 50 minutes. Okay, you have 50 minutes for this exam. So approximately you have 10 minutes or less for each of those problems. Okay, so that's kind of a short exam. Okay, so for the final, the size of the exam is going to be doubled. So you're going to have probably 10 to 12 problems, and you have 120 minutes to complete all your questions. Okay, so that's kind of for this exam. Now I would like to, we would like to talk about these problems on a slope field. Okay, so for example, here you can see the first question is like a blank filling multiple choice question, right? So the question says that, can you write a letter of the corresponding direction field for the differential equation? Okay, so first equation is y prime is y minus 1, y plus 2. Second question is equation is y prime is y plus 1 multiplied by y minus 2. Third equation is y prime is equal to 1 minus y plus multiplied by y plus 2. How do you choose the slope field? Well, in order to choose the slope field, you can see first that in all the three pictures, the slope field is going to be 0. That means the slope are going to be parallel to the x-axis. That means the slope is 0 at points y equal to 1 or y equal to minus 2. That's because for both, for all the three equations, right? So for all the three equations, the zeros of the right-hand side are y equal to 1 minus 2, y equal to 1 minus 2. Here the zeros is going to be y equal to minus 1 plus 2. So that means the minus 1 plus 2 is here in this picture. This one is not minus 1 and plus 2. So this must be B, because it is only the B equation is going to have 0 slope field at the point y equal to minus 1 or the point y equal to plus 2. So that must be B. So you can see that you really determine the slope field by simply observing some quantitative pictures, all right? So some qualitative pictures of the slope field, right? So for example, how do you distinguish A and C? Well, for A and C, you can see, although these zeros are the same, but the trend of the slope field is different. For example, in A, when y is between minus 2 and 1, the slope is positive. When y is between 0 and minus 2 and 1 in C, the slope is going to be negative. What happens to the equations, right? So for the first equation, if y is less than 1, that means this is negative, and y is larger than minus 2, this is positive, the multiplication is going to be negative. So you're going to point it downwards, right? So for C, you have flipped this sign, y minus 1, into 1 minus y. So that means it's positive. So that means this equation is for A, and this equation is for C. So that's a nice example, right? So that's a nice example about an application of slope field. Although you have not really solved the differential equation, but you can determine which differential equation corresponding to which direction field simply by looking at the trend, right? So simply by looking at the trend. By trend, it means positive, negative, or zeros of this direction field, right? So that's kind of a very simple exercise, but it's worth 18 points in the exam, right? So it's worth a lot. Now, what about the problem B? Okay, so for problem B, the question is going to ask you, can you, so based on the direction field given below, for such an equation, y prime is equal to f, t, and y, right? So some people might ask, you don't have x here, but it doesn't matter. As I said, for any differential equation, the most important thing is to determine which one is the function and which one is the variable. For example, this one, y is the function, t is the variable, right? So as long as you are aware of this, it means that your picture is in the ty plane, right? So as you want to find a y as a curve, which is the curve of the function of y, graph of the function of y as a function of t, right? So that's what you want to find. Now, can you sketch, suppose the direction field is given. Can you sketch the equilibrium solution? Okay, so I have not been talking about equilibrium solution. At that time, the syllabus contains equilibrium solution, but it doesn't matter. By equilibrium solution, I can tell you, it's just a solution that has a 0 slope. So the equilibrium solutions are here and here. So that's the equilibrium solutions, right? So, and through each given point, there are 3 given points, A, B, C. Can you draw a curve of this function, right? So, well, for A, you can see that must be increasing. You can just approximately draw it, right? Because the slope are positive. For B, the slope is negative, but it's negatively decreasing and then negatively increasing. So it's coming from 0, and it started gradually becomes more and more negative, and then it's starting to come back to be more and more to 0. So That's an S-shaped curve, somehow like this. What about C? Well, if you want to have a curve that passes through point C, it must be going from a zero slope and become more and more negative, so it goes down and hit the ground, right? So that's kind of the way how you draw a picture of the slope field. Okay, so how you draw a picture of the slope field. Okay, so this is a nice example about the slope field that I would like to talk about. And this is also the first time we see an exam problem for the course. Okay, so I would like to remind you that most of our lectures, okay, so for most of our lectures later or in this semester, okay, so I mean, essentially for the whole semester, everything will be quite like this. Okay, so everything will be quite like this. That means we're going to mostly working with those examples that we already had. Okay, so that we already had in the past year's exams, and we're going to work directly through them to help you to go over the exams that you're going to encounter for the new semester. Okay, so that's all I want to have for the slope field. Okay, so here I would like to pay several remarks. Okay, so I would like to pay several remarks to these problems. Okay, so the first remark I would like to say is that when you have a differential equation, the derivatives, okay, so of a differential equation may be represented as differentials. So that means there are several ways to write the differential equation. For example, you can say it's a derivative equation, so that means y prime is 3x squared. But then you can see that this is looking for a function of y as a function of x. So therefore, you must be able to write it as dy over dx is 3x squared. Okay, so that's a differential. That's really in a ratio of infinitesimal differentials of this equation. But the infinitesimal differentials can be moved around and treated as an algebraic object. So that means you can write this dy as 3x squared multiplied by dx. This is another way to write the differential equation. Okay, so this is kind of a very important point that you're going to see that soon see that it becomes very important for helping you. Okay, so helping you to understand differential equations. Okay, so and the second point I want to say is that our course is called an elementary differential equation. And by elementary, it means that we're not going to treat partial derivatives. Okay, so in your calculus class, you must have been encountering those functions that might depend on several different variables. For example, f depend on x, y, z, right? So several variables. If you want to have a differential equation like that, then it means that you're going to relate several partial derivatives into an equation. And this is not what we're going to talk about in these lectures. Okay, so this lecture is going to be simple, that we're going to call it an ordinary differential equation. By ordinary differential equation, that means you're going to have only one variable and one function. So you're looking for a function as a function of another variable. There's only one variable and one function that you're going to look for. Okay, so that's kind of the very simple thing that we're going to call elementary differential equation, but sometimes in more standard terminology, mathematical terminology, it is called ODEs. By ODE, it means ordinary differential equations. Okay, so by ODE, it means ordinary differential equations. So that's about ODEs. Okay, so, and the third point I would like to talk about, and you already see such a point in your previous calculations. For example, you can say that here I have an equation y in terms of x, right? So the very important thing is that y is a function of x, right? So dy over dx is something. So y is a function of x. But these variables are really dummy, right? So this, like in calculus, we've been talking about dummy variables. Dummy variables means that only the relations, okay, only the relations of the variables are going to be important, and the exact names of these variables are not going to be so important. For example, I can say the same equation is du over dv, 3v squared. So u as a function of v, right? So it doesn't matter how you call those variables, x, y, or uv. The only important thing is what's their relation. So these are essentially two same differential equations. So that means the variables are dummy, and this is sometimes very important, especially on the exams. You do not, please do not think so naively. For example, you always think of the function, let's say y as a function of x, it might happen that x as a function of y, right? So they might give you an equation, something like dx over dy. And you have to understand that x is now the variable and y is the, x is now the function and y is the variable. Right? So that's kind of, you have to be flexible with what you have learned from this class. So that's the third remark I would like to talk about. Okay, so that's the third remark I would like to talk about. So now for the rest about 8 minutes of today's lecture, actually I started a little bit late. All right, so we've been talking about our course rationale this at the very beginning of this class. Okay, so we may run a few minutes late. Okay, so now here we come back to the ordinary differential equations that we have been talking about on Monday's lecture, right? So on Monday's lecture, we've been talking about this prescription drug problem. Okay, so right, so on Monday's lecture, we've been talking about this equation. So that if you remember, it was describing. Okay, so it was describing the amount of drug in the person's bloodstream, right? So it was describing the amount of drug in the person's bloodstream, and the differential equation is established based on the principle that the net rate change of a certain quantity is the inflow minus the outflow. So as the differential equation is like dA over dt is equal to 500 minus 0.4 multiplied by 8. So that's the differential equation that we've been talking about, right? So on Monday's lecture. Okay, so now the question is, how are you going to solve this differential equation, right? So the question is, how are you going to solve this differential equation, right? So let me try to give you a way to solve this differential equation and finish today's lecture. Okay, so how are you going to solve this differential equation? Well, in order to solve this differential equation, you can see that it is not a kind of sometimes you can see that when you want to find a from the derivative of a by fundamental theorem of calculus, right? So we already have this fundamental, okay, so fundamental theorem, okay, so of calculus. It tells us, right? So fundamental theorem of calculus tells us that f of, let's say, x minus the f of 0 is equal to the integral from 0 to x of f prime of s ds. So that's fundamental theorem of calculus. So that means whenever you have a derivative of a function, you can recover this function from its derivative. So that means, in a certain sense, solving a differential equation, sometimes we call it integrating a differential equation, right? So that's, you just want to find a way that you can always apply the fundamental theorem of calculus and you recover the function from its derivative. So that's the major point of solving a differential equation, is that you want to find this solution, which is a function, from the derivative. But how can you do that for this example? Well, you can integrate, right? So if you integrate a of t, that means the integral from 0 to t dA over dt, right, of s ds, right? So you can, but this dA over dt is 0 to t 500, right? So let's say 500 minus, right? So 500 minus, right? So 500, and then it's going to be minus 0.4 of a, and then ds. Now you have a problem because you're having an a of t, you're having an a of t here, right? So you're looking for a function a of t as the integration of the same unknown function. So that's kind of a tautological fact that doesn't give you anything, because it tells you that a function is equal to its integral, right? So it doesn't really tell you anything. So what's the problem? The problem is that the right-hand side of this function equation depends on the unknown variable also. So that's the problem, right? So how are we going to solve this differential equation? Well, the idea is very simple. We're not going to treat dA over dt as a derivative, but rather we're going to treat it as a ratio of infinitesimals. Okay, so if it is a ratio of infinitesimals, it can be moved around. So that means the same equation can be written as dA is equal to 500 minus 0.4 of a multiplied by dt. I can write everything like this, right? So that's, I multiply dt to the right-hand side. And in the same rationale, it can be written as dA over 500 minus 0.4 of a is equal to dt. And now you can see that both the left-hand side and right-hand side are infinitesimal differentials for a and t respectively. So that means you can integrate. So if you have the differentials are the same, then the antiderivatives are the same. So basically, it means that 500 minus 0.4 of a integrated is equal to the integral over dt. Right? So you're going to have some kind of relation like this. Okay, so this is like what we have been showing here, right? So once you have this relation, you can integrate on both sides. Okay, you can integrate on both sides. Now let me remind you that in our course webpage, okay, so if you go to the student resources webpage, as I just explained, you do browse more courses, you go to student resources webpage, right? So go to student resource. You're going to find this 3304 integral formulas. Okay, so let me tell you that on the exams of this class, okay, we're not allowed to use calculators, nor are we allowed to use these integral formulas. Okay, so you're not allowed to bring these integral formulas into the exam. Then people ask why you need this integral formula. Well, this is just to help you to remember what you have learned in your calculus class, right? So, for example, here we have encountered such a problem, namely, how do you calculate the integral of 1 over x, right? So 500 minus 0.4 of a, you can always do a change of variable to return it to 1 over x. Now, what's the antiderivative of 1 over x? Well, the antiderivative of 1 over x can be found in this integral formula, which is here. The integral of du over u is logarithm. Remember, it's the absolute value of u. You cannot ignore the absolute value in the logarithm, right? And then plus a constant. So by this, you can see that here, via a change of variable, okay, so I'm not going to carefully do it, but via change of variable, you are going to see that by this antiderivative formula, you're going to end up with this formula. Okay, so that means minus 1 over 0.4. Okay, so that's the same thing as saying that minus 1 over 0.4 of logarithm, but with the absolute value 500 minus 0.4 of a plus a constant is equal to t, right? So antiderivative dt is t plus another constant c2, right? So you're going to have such a relation between the antiderivatives of the logarithms, right? So you have this relation t plus c2. Okay, so that also kind of gives us such a phenomenon. Okay, so such a phenomenon that on a differential equation, when you integrate this differential equation, you are looking for the antiderivatives. And once you have the antiderivatives, there might be some unknown constants that's going to appear in this equation, right? So there might be some constants that's going to appear in this differential equation. Now, let me say that, let me ask, do I need both constants C1 and C2? The answer is no, because this equation is just an equality. So it just tells you that 0.4, okay, of the logarithm of 500 minus 0.4 of a is just equal to what? It is just equal to t, okay, so plus C2 minus the C1. But what is C2 minus C1? C2 minus C1, if C1 and C2 are constants, C2 minus C1 is another constant. So the whole equation, we do not really need two different constants, but just one constant C, right? So, but just one constant C. So that means you actually have this relation, logarithm of 500 minus 0.4 of A is equal to minus 0.4 of T plus minus 0.4 of C. But then you're going to come to the same question. If C is a constant, then minus 0.4 multiplied by C is again a constant. So you really can vary. Okay, so it means that these constants, they really vary from line to line, right? So I can have one constant C, but another constant C in a different line. So the constants are vary from line to line, right? So constants are vary from line to line. Now, once you have that, you can see that you can further raise 500 minus 0.4 of A in absolute value to be e power of minus 0.4 of t. Again, you're raising this problem because it is a plus c. It means you're multiplying e to the power of c, right? So, but e to the power of c, if c is a constant, e to the power of c is again a constant. And if it is a constant, I can use another constant k to represent this quantity k, right? So that's kind of, you really have this constants, from constants to constants, you're changing it, right? So in the end, once you have that k, you find a solution, right? So you find a solution to your problem. Okay, so now you can see that further, for example here, it's going to tell you that 500 minus 0.4 of a is like a plus minus of k and e power minus 0.4 of t. Do I need a plus and minus? Well, if plus k is a constant, then minus k is another constant. So indeed, because these are both constants, you can ignore the plus minus. You can just say, I have a k, which is some kind of constant. So in the end, your solution is going to look like, okay, so in the end, you're going to find a solution that's going to look like 1,250, right? So if you just work out this algebra, it's 1,250 minus 0.4 minus k, right? So, sorry, so minus the k, right? So minus the k multiplied by e power, okay, so minus 0.4 of t, right? So that's k multiplied by e power, okay, so 0.4 of t. Now, some people ask, why do you have another k? It looks like a k has to be divided by 0.4, but it doesn't matter, right? So it will be another k. So this k is not exactly, so you can see that when you solve a differential equation, typical phenomenon that occurs is that you're going to have constants vary from line to line. And finally, you have a solution. This is a solution that models the amount of drug in a person's bloodstream as a function of t, but it involves such a constant k. Okay. So now let me stop today's lecture at this point. Okay. So let me stop the lecture here, and we're going to continue with the discussion on this differential equation on Friday's lecture. Okay. So and I will see you in the next lecture. Okay. So. And that's all for today. Okay, so thank you for participating.